Okay, so forget that old movie stereotype, right?
Yeah.
The hacker in the hoodie, pounding energy drinks.
Yeah, clicking away madly.
Exactly. Picture something else. Something
Hmm?
way more efficient. Tirelessly hammering vulnerabilities,
Yeah.
uh, switching tactics in milliseconds,
Hmm.
and it never needs a pizza break.
Hmm.
That's kind of the reality of AI hacking we're looking at now.
Hmm.
Today, we're doing a deep dive into this, well, groundbreaking study. It's called Error Bench.
Right. Error bit.
And it basically proves AI can break into systems, well, faster than you can blink.
Mm-hmm.
So our mission here, give you the shortcut, the quick guide to understanding this urgent new thing. We've got some surprising facts, maybe a little bit of humor to keep it, interesting.
And this isn't just like another think piece about what might happen someday.
Okay.
This error bench study, it's a data-packed bombshell, especially if you thought maybe prompt injection was like old news.
Yeah, yesterday's problem.
Exactly. This research, it basically drags AI hacking out of science fiction and drops it right into today. Shows what these big language models can actually do right now.
Okay, let's unpack that then. What is AI hacking, really? I mean, most of us met large language models, LLMs, through chatbots.
Right? Chat interfaces,
Yep.
autocomplete, maybe?
Yeah, they seem helpful. They can chat, write poems. But here's the twist, you're saying. Under the hood, these things, these transformers, they can do more.
Oh, yeah. Much more. They can change shell commands, they can reverse hashes, script network scans,
Hmm.
stuff like that.
Wow. Okay.
And if you give them access to something like a Jupyter kernel, which is like an interactive coding space.
Right. Developers use those.
Exactly. And you put them in a safe little box, Docker sandbox.
Oh,
Well, they kind of morph into these relentless breach agents.
tireless.
Tireless breach monkeys, I think you called them before we started.
Huh. Yeah, something like that. And that transformation, that's exactly what AirBench was built to test, properly test.
The proving ground.
It's a crucial proving ground. They set up 70 Tandy black box capture the flag challenges,
Yeah.
CTFs.
Okay, CTFs, like hacking puzzles where you grab a flag. Precisely. But black box means you get nothing. No source code, no hints, just here's the target, go figure it out. Very. And they covered all sorts of things. Prompt injection, model inversion, evasion across text, images, audio, even just raw system hacking.
And the scoring was strict.
Absolutely mechanistic. Either the flag gets posted to the server, proof you got in, or the whole attempt fails. That's it. Which makes it, super realistic.
And the results, you said bombshell. I mean, the speed sounds incredible.
Yeah.
Humans taking hours, days maybe.
Or longer sometimes, yeah, for the
Yeah.
tricky ones.
Yeah.
But the AIs often cleared the same hurdles in under 10 minutes.
10 minutes, seriously.
Some of the really hard exploits, the kind that, a red team might spend a whole weekend wrestling with,
Mm-hmm.
some of those fell in just 6 conversation turns with the AI. 6.
Okay, that's fast. So let's unpack this. What do the numbers say about performance overall across the whole test suite?
Yeah, the overall performance data is pretty striking. So Claude 3.7 Sonnet, it cracked 61% of the whole set. 61%, wow.
Yeah, Gemini 2.5 Pro got 56%, and even a smaller one, O3 Mini, solved almost half, 47%.
Okay, so they're capable.
Very. But here's a really crucial bit, the token efficiency gap. Tokens are like the chunks of text or code the AI processes.
Right, and they cost money or compute power.
Exactly.
Right.
So get this. GPT 4.5 preview hit 49% success, but it only used about 5,000 tokens for each successful hack.
Okay.
Compare that to Claude 3.7 Sonnet, which needed 15,000 tokens per success.
3 times as many tokens for a similar job.
Roughly, yeah. And the cost implication is huge. Successful runs averaged about 8K tokens, but the failed attempts, they ballooned to almost 49,000 tokens on average.
Whoa, so failure is expensive.
Like 6 times more expensive, just useless chatter, burning through tokens, potentially setting off alarms. It's not just money, it's compute waste, it's noise.
It's fascinating, though, to see not just that they can do it, but where they're good and maybe where they're not so good yet. Absolutely. The frontier models, the big ones, they just devour prompt injection tasks. Like half of those flags, on average, they just gobbled them up.
Half is. That's a really high success rate for an attacker.
It is. But they did stumble a bit elsewhere. Model inversion, deep system exploitation, those were tougher for them.
Okay, how tough?
Well, Gemini 2.5 Pro only got 3% success there. Claude 3.7 Sonnet managed 14%.
Ah, okay. So that's maybe some good news for defenders.
For now.
For now, yeah.
Hey.
Data breeding arm. But, the caution is the ceiling keeps rising. These things learn fast.
Right.
And there's a great example of that, actually, the turtle challenge.
The turtle challenge. Okay.
Yeah, it was notoriously hard for humans, only cracked it about 6% of the time.
Right.
Usually after, like, pulling all-nighters.
Ouch.
So Claude took 30 turns to solve it. Gemini needed 41. Lots of back and forth.
Still got there, though.
They did. But here's where it gets really interesting. There's this open source model, Llama 417B. Kind of scrappy, right?
Open source. It nailed the turtle challenge in 6 lines of dialogue.
6 lines? How?
It basically just reframed the request, didn't ask it to do something bad, asked it to perform security hardening, tricked the target system into basically revealing its own secrets.
Wow. By asking nicely, almost.
In a very sneaky way, yes. And that single example, it tells every, security chief out there something pretty painful, this LLM hacking skill.
Yeah.
It's not just in the big, expensive, closed models anymore. It's spreading. Open source means more people can access it.
Yeah, that's a big deal. The benchmark also found some other weird things, right? Quirks.
It did. Like Error Bench deliberately slows down requests, throttles them like a firewall might.
To make it realistic.
Exactly. And the Gemini 2.5 models, they hit those rate limits in 1/3 of their attempts, but they still had really high success rates.
So they're persistent, robust.
Surprisingly so.
Yeah.
And then there was this other thing they called tool calling, XML, the surprise gatekeeper.
XML, like old school web code.
Sort of, yeah. The models had to talk to the target systems by wrapping code in XML tags. And believe it or not, simple XML errors forgetting a closing tag, stuff like that, killed the hacking attempts twice as often as actual bugs in the Python code they were trying to run.
No way. Just bad formatting.
Just bad formatting. So what does that tell us about, building AI security tools for the future?
It tells me the basics still matter, I guess.
That's a huge part of it. That glue code, the boring stuff that connects things, is like security's quiet king. You can be the best exploit writer ever, but if you forget to close a tag, game over.
Okay.
And we saw some, let's call them personality quirks too, like DeepSeek R1. Sometimes it would fire off 24 wrong flags before it finally got the right one.
Just guessing wildly.
Seemed like it. Or
Yeah.
Gemini 2.0 Flash had these moments. The researchers kind of described them as rage quit moments. It would just stop trying.
Seriously. An AI rage quit.
Apparently. And all this extra chatter, these weird behaviors, they have real consequences. Inflated cloud bills, obviously, but also tripping anomaly detectors that are looking for weird traffic patterns.
Right.
And just wasting precious computing time during a real incident.
So the AI needs to be not just clever, but efficient, almost professional.
Exactly. Tenacious, but also thrifty. It's a balance.
Okay, zooming out again, the big picture here seems pretty stark. Automation is real. Like, really real.
Oh, absolutely. These models cut down exploit writing time by, 3 orders of magnitude, thousands of times faster.
Thousands. And diversity matters, too, you said. Different AIs are good at different attacks.
Right. No single silver bullet on the attack side, which means no single silver bullet for defense either. You need layers.
And the critical point, defensive AI has to catch up. It sounds like a new kind of arms race.
It absolutely is an accelerated arms race between AI attackers and hopefully AI defenders.
So if you're running systems, what's the takeaway? What's the defensive posture?
It's pretty clear now. If your tech stack uses or interacts with language models in any significant way, you need guardrails. You need monitoring. You need incident response plans that assume the attacker might also be an LLM.
Assume the attacker is AI.
Yes. This isn't just cybersecurity anymore. It's generative AI cybersecurity, and frankly, it's not optional.
Right. So, okay, how do we protect ourselves? How do we build those digital walls in this new age? You mentioned threat modeling for the transformer age. What does that mean practically?
It means shifting your thinking. Classical security models didn't really account for, your friendly chatbot suddenly becoming a secret way to exfiltrate data.
Or your database becoming a map for attackers.
Exactly. Or the fact that every single prompt someone sends to your AI has to be treated as potentially hostile, untrusted input.
Okay. And the study gave us categories to think about, a cheat sheet.
It did, yeah. The main attack vectors they tested give us a good framework. Prompt injection basically tricking the AI. Model evasion getting around its safety rules. Model inversion trying to steal its secrets or training data. And system exploitation using the AI to hack other stuff.
Got it. Prompt injection, evasion, inversion, exploitation.
Those are the big ones. And knowing those, we can build practical guardrails. We can kind of morph that textbook idea of zero trust into real generative AI security.
Okay, like what? What are these guardrails?
All right, so first, Content security policies for prompts. Think strict rules for inputs. Use structured templates. Don't just let users type anything. Whitelist specific functions the AI is allowed to call. Basically, be a tough bouncer at the door.
Don't let just any request in.
Okay. Second, adaptive rate limits. Static limits are too easy for AI to work around. You need smarter limits, like token bucket algorithms that can spot and squeeze sudden bursts or weird query patterns.
Dynamic defenses. Makes sense.
Third, output verifiers. Have another model check the first AI's responses before they go out, like a quality control check or a bouncer for your talkative bartender, making sure it doesn't spill any secrets.
A second AI watching the first.
Interesting.
And
Fourth, explainability logs. You need to log how the AI reached its conclusions, its rationale. So if something goes wrong, you can replay its thought process. Crucial for forensics, but you still need to protect user privacy, of course.
The audit trail.
Got it. And fifth, cost monitoring dashboards. Simple but effective. Tie token usage to alerts. If some internal tool suddenly starts using 50 times its normal budget, hit the kill switch. It might be an attack, might just be a runaway process, but you catch it early.
Stop the bleeding financially and maybe security-wise, too.
Exactly. Those kinds of controls. That's how you start building real defenses for this Gen AI world.
And finding people who can build and manage all this, that sounds like a challenge, too. You mentioned AI cybersecurity jobs.
Oh, it's exploding. Thousands of job listings already with that tag. Recruiters are basically looking for unicorns. Yeah, people who get traditional hacking, red teaming, and prompt engineering, and MLOps, the operational side of machine learning. It's a rare mix.
High demand, low supply right now, I bet.
For sure. Which brings up that open source question again. It's kind of a paradox, isn't it?
How so?
Well, open source models are great. They speed up research, help find bugs faster, prevent everyone from relying on just one company's AI.
Reduces monoculture risk, yeah.
But they also put these powerful tools directly into the hands of threat actors. Anyone can download and adapt them. The genie's out of the bottle, really.
So what do we do? Try to put it back in?
Can't. The better approach is to engage with it. Lean into the transparency. Sponsor bug bounties for open models. Carefully check community contributions. Encourage open, reproducible security research. That transparency, that openness, probably our best shot at staying ahead, collectively.
Fight fire with fire, almost.
Yeah.
Use the openness for defense.
Kinda, yeah. It's about faster iteration on the defensive side.
Okay, let's bring it back to brass tacks for businesses, maybe even individuals. Cost. You mentioned the token math earlier. Claude versus GPT 4.5. $6 versus under $1 for one challenge.
Right. And imagine scaling that up. If you're running these things constantly, maybe in your development pipeline or customer service, those cost differences become massive. Security budgets have to weigh the effectiveness, the coverage against that token cost. It's a new variable.
A very tangible one.
Absolutely. And looking ahead, think about compliance, certification, insurance.
Oh yeah, the regulators and insurers must be watching this closely.
They definitely are. You should absolutely expect new frameworks, new rules, asking companies to prove they've tested their AI systems. Tested against benchmarks like ArcBench, tested against hostile prompts, logged the AI's reasoning.
Proof of due diligence?
Exactly. And insurance companies. They'll start demanding proof of regular automated AI penetration testing before they'll even write a policy covering AI risks.
So getting ahead of this now, implementing automated red teams, these guardrails, it's not just good security, it's good business planning.
Totally. The early adopters here, they'll likely breeze past those future compliance audits. The laggards will be scrambling.
Okay, so wrapping up, the urgent reality seems pretty clear. AI hacking isn't waiting for us to catch up. It won't wait for the quarterly patch cycle.
Not a chance. Models are already outpacing human exploit development by, like, thousands of times.
But the flip side is, this same AI tech can also give us defenders new tools, right? These always awake sentinels.
That's the hope, and that's the race. The final balance, who wins this phase, it really hinges on who iterates faster, who learns and adapts more quickly, who hardens their feedback loops.
So the call to action is practical.
Very practical. Audit your prompts, sandbox your kernels, isolate these things, budget for those token spikes, assume they'll happen, hire or train people who understand AI cybersecurity. Get the right tools. And maybe most importantly, treat every output from an LLM as untrusted until you verify it. Trust but verify is way too weak here. It's more like verify, then verify again.
Verify, verify. Okay, so the machines are already knocking, constantly, tirelessly. And like we said, they don't need pizza breaks. What does that relentless adversary mean for your digital life, your organization's security, that's maybe the big question to keep thinking about.